Hello everyone, I am Animesh Garg and I am an assistant professor at University of Toronto. I study algorithmic methods to enable efficient robot learning and manipulation. The aim is to build autonomous systems to operate in unstructured and open world settings. And as a researcher in robotics, it is my dream to achieve out-of-the-box autonomy as is often promised to us by science fiction and cartoons. And if we think of a system that I just described, we would want it to do a variety of activities. It may involve vacuuming, sweeping, cooking, laundry, perhaps do more than what you do with a single robot or in a single task. And in fact, we would want it to do these things not just in the lab settings, but perhaps in my home, your home. And for that, it needs to be able to adapt to diversity that handles new scenes or uses new objects as tools, and perhaps solves newer tasks which are more complex than what the system has been exposed to in controlled settings. This brings us to the vision of my research agenda is to build these robotic systems, rather robotic companions, and the hope is to extend the human ability both cognitively and physically. However, this has been the goal of robotics ever since we have started doing artificial intelligence. The term artificial intelligence was coined in 1956, and soon after, we had a system in 1968 where we were attempting to build robotic kitchen assistants. The robot here is rather large, but the system is essentially doing what we would love to do with our robots today, make us breakfast. Now, if we jump fast forward to 50 years, that is this year, this is a video that is built by Sony at CES this year. CES is Consumer Electronics Show. And what is striking, even after 50 years of progress in this domain, we still have these scripted videos that are still concept videos. What is it that is stopping us from building such systems? It turns out that we have had a lot of progress in building real world robots with very good hardware rather. But when you put these real world systems with real perception in the real world, it doesn't work really well. Not surprisingly, handling new unstructured environments is really hard. So the question that we're asking is, what gives? What will it take for us to achieve this vision? And my argument is to generalize to unstructured scenarios and scenes is the key question here. I've used cooking and home robots as an example so far, but there's nothing particularly special in that domain. This generalization or lack thereof really exists in manufacturing, retail, personal robotics, and even healthcare and medicine. So that brings us to the question of how do we approach this problem? And I argue that we need to build abstractions and learning algorithms that inject structured inductive bias and priors to achieve this generalization. This constitutes two steps. The first one involves efficient skill learning. The system learns to do the task in the same setup using instructional input. Thereafter, we need mechanisms that achieve generalization through self-improvement. However, this idea of imitation is often looked down upon. I would argue that imitation is actually very layered. It is not easy to copy. So let's assume that you have a mechanism to provide data, let's say through some sort of task specification. The first order of imitation can be actually control, where you're trying to attempt to match the movement skills. It may or may not complete the task, but that's the first stage of imitation. As you grow up, you actually start to understand how planning works. So you can actually do skill sequencing to do longer term imitation. And as you grow up even beyond that, you understand that there is a semantic purpose to the task. In this particular case, it's really collecting leaves. So it doesn't matter if you have the same broom or not. You can actually try to do this with a different set of tools. So adding perception to the loop and adding semantics in the setup allows us to do imitation that is purposive. And I argue that to build any sort of practical system, we have to think about these problems broadly in a manner that is holistic. We have to think about how to unify control, perception, and planning along with big data such that we can understand and, and build systems that leverage learning in all of these interactions. And along with these core methods, we can build transformative applications in all of the examples that I mentioned, starting from home to manufacturing and retail and healthcare and surgery. So today, I will actually go about talking about algorithms that we have built in the last few years in all four of these domains. And I'll give you one particular example in each of these domains to sort of convince you that how these areas are very tightly integrated. So let's start with control. So the challenge in this case, as we started with, is we want to build a single algorithm or unified algorithm that can handle all sorts of activities without us recoding an algorithm or redesigning an algorithm for each of these things. And the argument can be that we would really want to build systems that can handle these activities from a Visuo-Motor perspective, where the input is vision, while the output is control, so that we don't have to build particular visual perception schemes. So let's start with an example of cleaning. And let's say the task specification is maybe cleaning the radios. Perhaps we are not cleaning radios very much these days, but nonetheless. The question is, how would such a skill of cleaning a surface generalize? You might want to clean a whiteboard. Perhaps you might want to clean harder stains that require you to push harder, or maybe you need to push gently because you don't want to break the glass itself. So how would we do this task currently? One approach to do this is actually deep reinforcement learning. Here, the policy takes an image as input and outputs joint torques. These methods have been applied to a variety of skill learning use cases. And the method is actually agnostic in the sense that it needs no environment model. However, these tasks are very sample inefficient, since they need to learn the robot model as well, and rather brittle to changes between training and test setup, essentially overfitting to training tasks. Now, on the contrary, we can build a solution out of a model-based approach. Here, we can treat the robot end effector as a point mass and convert the desired end effector state to a robot joint state with the robot model. However, setting the desired state requires a model of the task to schedule these gain parameters. An explicit state is often very task specific. So the key insight here is that we can get best of both worlds. By creating a compositional schema, the model-free RL policy sets the desired state, and a deterministic robot model then converts it to joint torques. And the important thing here to understand is the natural choice of action space of the policy. It outputs not only the pose and the velocity, but also dynamically sets the impedance gains. It enables the policy to learn to schedule these gains during different phases of the task. And this compositional approach makes policy learning easier because the robot model is given, while the policy learning still lacks the task constraints in image space. This enables better sample efficiency and also transfer, as I will show later. So for evaluation, we consider this task of wiping a surface. In this case, the inset picture shows what the robot observes. The reward model is fairly simple, which is basically clean the table and do not harm the robot without applying too much force. And the key thing to note here is the performance gap between our model, which is variable impedance in end effector space, versus controlling direct joint torques. Other baselines lie in between, but essentially that's the difference between success and failure after 1 million steps of interaction. And the video here shows the performance qualitatively. Using a similar idea, we can actually now follow the transfer to a real robot as well. Interestingly, this succeeds about 80% of the time right out of the box. And if we look at the gains during the task, what is really happening in this case is you can learn a policy purely in a simulation, and when you go to the real world, by replacing the outer loop or the function f, you can perform this transfer without doing any particular training on the real robot. So in this case, the takeaway is really that action representations in learning provide structure to the learning process, which in turn yields improved generalization. So let's move to planning now. In planning, let's consider tasks which require us to do more than just single tasks such as surface wiping. This was an example where I showed you primitive tasks with RL, but many tasks require sequential decision making, something like tool use. We have to decide where to grasp and then how to use the tool. So let us consider this simple task of sweeping and hammering. We aim to perform these tasks using novel objects without object classification or 3D models of the objects. And the same object can be grasped by the robot in different ways. A task-agnostic model can lift up the hammer, but it might actually be not suitable for either of these tasks. In fact, what we need is to generate grasps, the right grasp rather, for the right task directly by optimizing for task success rather than optimizing a surrogate objective, which is just grasp success. Concretely, given an input image with a new object in a task, we need to compute how to grab the object or grasp the object and then a policy to use it. However, directly solving this problem results in discrete search space over a large space of grasps, and then a subsequent optimization problem to solve for a manipulation policy given each grasp. But we observe that the task only succeeds if the task grasp succeeds. The other way around is actually not true. This enables us to factorize this score in two quantities, a task conditional grasp and a grasp success model. Given this factorization, the system enables us to train jointly for task-oriented grasping and a manipulation policy. The loss for grasping in this case is computed using cross-entropy loss, and while the policy is trained with policy gradients. To generalize to unseen objects, we create a set of 18,000 procedurally generated diverse objects and train the model purely in simulation with self-supervision. At inference time, we get a depth image as an observation. This is possibly an unseen object. We sample the grasp candidates, and depending on the task, the grasps are ranked according to prediction of the task-oriented grasping model. And then the manipulation policy outputs actions conditioned on the selected grasp. Here we show qualitative results of the model performing these tasks on new objects that were not in the training set. And quantitatively, we compare our jointly optimized model with a heuristic model for grasping, a two-stage pipeline which optimizes grasping and manipulation separately, and our model. And in both these cases, hammering and sweeping, we observe that we perform substantially better. Since the input is a depth image, we can transfer this model to a real robot without fine-tuning. We evaluate on 9 novel objects, and we observe a significant performance gain due to joint optimization in both hammering and also the sweeping case. So moving on, we showed you examples of how we can do two-stage tasks such as hammering. However, many skills may require us to think about longer-term reasoning. Consider this task where a peg needs to be rolled closer to the user. However, the peg should not roll off the table. Hence, the user needs to use the objects on the table as assistive systems. Now, such problem solving, especially with new objects or unseen objects of unknown shape, requires multi-step reasoning. So the question that we are asking is, can a robot efficiently learn to perform multi-step manipulation tasks under various physical and semantic constraints? And we attempt to study this question in a manipulation setting where the robot is asked to move a target object to a goal position with a stick. Now, the physical constraint here is that the target object is required to move across the bridge step by step, as denoted by gray tiles. And if the target leaves the bridge, the task will fail. The problem becomes even more challenging when multiple novel objects are placed on the table. In presence of an obstacle, two decisions must be made: a non-greedy discrete decision on which object to push, and then a continuous space decision where to push it. Once the path is clear, the robot can decide to attend to the target object and push it to the goal. Building a system like this has often been relied on model-based approaches. Key to such approaches is actually learning a dynamics-based model that is used to predict resultant states given sampled action, and then an optimal action sequence can be selected by unrolling the dynamics model until achieving the task goal. However, it is non-trivial in these kind of setups to build this system with model-based methods. Model-based learning methods rely on combining image-based dynamics, have enjoyed some success in recent times. But this is a general solution where, as the complexity of the task grows, the requirement of the data grows exponentially. So a simplistic approach like this may not always scale to more complex tasks of multi-step manipulation. To this end, we have proposed a cabin planner to hierarchically generate plans in learned latent space. The two latent codes, the effect code and the motion code, are learned to facilitate planning. And the key insight here is to take advantage of the hierarchical structure of the action space, long-term effect and local motion, such that the generation of action sequence can be factorized into two-level process. First, we perform high-level planning to select the desired state in terms of subgoals. Then we perform low-level planning for detailed actions that lead to chosen subgoals. The distribution of reachable subgoals at each step depends on the physical properties and spatial relationships of objects. For high-level planning, we introduce a metadynamics model to capture the subgoal distribution while abstracting away the detailed motions. We then predict cumulative rewards of each sequence of subgoals and choose the subgoal code C that leads to the task goal. For low-level planning, we introduce an action generator which uses both the latent codes C and Z. Conditioned on the current state and a chosen C, the action generator maps the motion code Z to a plausible action sequence that will push the object towards the next subgoal. The low-level learned dynamics model is used to evaluate the generated plans by predicting the resultant states. The action sequence that reaches the subgoal with higher reward will be executed. The model is trained with task-agnostic interactions in simulation. A heuristic policy controls the robot pushing randomly sampled objects on the table without task rewards. Since the latent codes cannot be observed in training data, we proposed a cascaded variational inference algorithm to learn the metadynamics model and the action generator. The two inference modules shown at the bottom are used to infer the latent codes from observed variables. In this particular case, the task environment involves a 7-Sawyer arm with a short stick, and up to 5 objects are placed randomly at the table in the beginning of each episode. Visual observations are then converted into a relational representation, and our module then produces coordinates of each pushing action. Every 3 time steps, the robot moves the arm out of the camera view to take a clean observation for replanning. We devise 3 manipulation tasks which involve multi-step manipulation. In addition to the crossing task that we've already talked about, the insertion task requires the robot to move the target object to a goal position without traversing a restricted area that is indicated by red tiles. And then the clearing task requires the robot to clear all objects within a region on the table indicated by blue tiles. In simulation, we compare our baselines which plan in the original space or plan in the latent space without a hierarchy we observed that our model achieves superior performance in terms of task success rate. And the performance gap is even larger when we are given sparse rewards. We also evaluated our model on the real robot environment while achieving similar success rates as simulated training. Hierarchical latent space dynamics model performs better with less reward signal. That is really the crux of this algorithm. Now let me show you some qualitative results. In this case, we observe that the robot comes up with diverse strategies for tasks in different scenarios, such as moving away obstacles along the path of a target object. In this particular case, for the insertion task, the system decides to go around a set of obstacles. In this particular case, instead of going around, it actually creates a path for the target object to be pushed into the slot. So really, the key insight from this line of work is that compositional priors from self-supervision and structured latent variable models lead to good representations that generalize. We saw this thing both in the cases of task-oriented grasping and then also in hierarchical latent variable models. Moving on to task structure, let's look at slightly more complex tasks that are longer than two-stage tasks. So in this particular case, we would want to do tasks that may require tree-structured latent space. So on the other hand, on one hand, we could try RL for these kind of tasks, but as we've already discussed, that RL can actually be sample inefficient, and even more so in structured multi-step delayed reward tasks. And for long-term tasks, one could argue that we could do imitation learning, but providing the correct task segmentation is actually a challenge. And these methods cannot handle variations in permutations of primitives at test time. So what we really want is meta-imitation learning, where we can do the task at test time with a single example and possibly operate directly with visual input. So what we mean concretely here is, instead of solving a single task, we would ideally like to solve multiple tasks in a given domain. To study hierarchical tasks in a rigid body manipulation, let's consider block stacking. It is a rich domain that captures the gist of these challenges. We can supervise the demonstration with demonstrations for a training set of tasks. And at test time, ideally, we want to be able to complete an unseen task with a single demonstration. Now, this problem has been studied in the past with one-shot imitation and has received quite a lot of attention in the deep RL community. But these techniques often model the input demonstration as a flat sequence encoded with a recurrent model. We want to explicitly leverage compositional structure both in the supervisory signal and also in the model itself. Now, consider the task of moving this red block on the blue block. Traditionally, we would write a program to complete a task like this. And given a new task instance, we would need to write another program for the new instance. We use this insight to formulate this RL problem as a supervised learning problem that is a program induction problem. The training inputs here consist of the demonstration along with a current state information and present program that is being executed currently and outputs the next subroutine and its arguments. Neural task programming, which is program induction as hierarchical policy learning, keeps predicting subroutines recursively until the bottom level program that is predicted is a robot API level command. The model is trained with supervision from ground truth hierarchical program trace, and the key underlying idea is to learn usable representations that are shared across tasks in a given domain. Here we see a detailed rollout of NTP in a block stacking task. We see that it begins with a high-level program of block stacking. It outputs the next step should be pick and place. The pick program is then further decomposed into a move to program and a grip program. These are primitive programs so that NTP predicts the arguments that primitive program should take. In this case, this is block E. So the first primitive program, move to, takes a blue block as input and proceeds to interact with the environment and executing the primitive that is When this primitive succeeds, the pointer or the program counter goes back to pick, where pick moves on to the grasp part of the task, where now the blue block is grasped, and the pointer goes back to pick and place and moves to the place part of the task. Similarly, decomposing this place part of the task, you now go to another move to block, which when completes results in the next move to and release, which would be releasing it in a particular position. Notice once place finishes, the program counter goes back to pick and place, which goes back to block stacking, and block stacking itself can continue. This is just one example of a pick and place, but in realistic settings, in experiments, we used instances where more than 40 pick and place operations needed to be performed in sequence. One thing to note here is what this process really enables. Here we see NTP take as input a demonstration of new block stacking task from simulation. NTP then instantiates a task condition policy that interacts with the real environment to complete this task, given some random initial conditions. And notice really what is important here is the ordering or the permutation of these tasks or the blocks. We highlight that neural task programming is a closed loop feedback policy and thus is able to recover from intermediate failures in the task. In this particular example of block stacking, we see that the blocks are knocked over in the middle due to an environment stochasticity or an adversarial agent. And given the state input, NTP reactively replans to redo the previous components of the task rather than just parsing the input as a sequence of actions. Continuing, we look at some results that are comparing this model quantitatively with a flat policy. In this particular case, what we see is when we compare NTP to new tasks, the flat policy, which was memorizing these trained tasks, really fails in the face of new tasks. On the contrary, with full state input, neural task programming performs surprisingly well even for new task permutations. More interestingly, when we train this model purely with vision input, we see that our system with a detector is using a pose estimator and then a planner, performs reasonably well. But then if we build the system with an end-to-end model, we can actually double the performance. The real takeaway here is that we can get better generalization than a flat policy, and we can train the system end-to-end with a visual perception module without having to estimate task-specific or domain-specific visual performance or visual states. In this case, those would be pose estimates. However, this system doesn't work everywhere. As we notice here, that the system can fail in places where the end conditions of low-level robot API are not handled properly. So to look over this problem, we went back to our system to understand what is going wrong. We noticed that while we are providing structure at the input-output level, the model itself is actually a black box. We can, in a manner of speaking, open this black box and insert an explicit compositional prior on the model to improve this process of neural task programming. This leads to a follow-up work that we did, which is called neural task graphs. The key idea here is to use task graph as an intermediate representation inside the neural network to improve generalization. There are two components to this model. The first is a task graph generator, which takes in as a video as input as before, and parses action sequence, and then adds new edges based on domain knowledge from other examples. The second part of the system is a task graph executor, which looks at the current state of the graph and decides what is the next action to give to the policy. A very interesting point here is actually the representation of the task graph. In the commonly used form, nodes correspond to states and edges correspond to actions. But this results in an intractable graph, since the common there are combinatorially many nodes, especially if states are images. So we propose to use a conjugate graph. Here, nodes represent actions and edges correspond to a set of valid states that enable transitions. This is similar to preconditions for an action. Because actions come from a fixed, finite set of high-level commands, we have actually a tractable representation here, making the whole representation finite. Now, during inference, a node localizer looks at the current observation and identifies the current action and maps it to a node in the task graph. Then an edge classifier selects an outgoing edge, which in turn results in the next action. The training of NTG is similar to NTP, except now we do not need full hierarchical supervision, but only a sequence of actions, which is much easier to recover. The hierarchy here is implicit. So if we go back to the same set of evaluations we performed for neural task programming, we can now see that with full state information, NTG performs very similarly to NTP. But with visual input, we really see that NTG outperforms by a big margin. The key underlying idea here is modeling the task structure explicitly as a graph provides a strong prior on the input sequences, which enables better generalization even with weaker supervision. These models have actually been applied to other tasks such as sorting, cleaning dinner tables, and sequential search tasks in navigation environments as well. So the key takeaway here is that compositional priors, such as neural programs and task graphs, provide a modular structure that is needed to achieve one-shot generalization to long-term sequential planning tasks. Finally, I want to talk to you about the data requirement in all of these domains. So we talked about algorithms at 3 different levels of abstractions. And data is really fuel to all of these learning algorithms. But what we noticed is as the complexity of the structure grew, the data set kept shrinking. But to scale to more complex tasks in next phases, we would need larger data sets with structured supervision. But the real question is how? So RL and self-supervised learning have shown to use large data set, but a lot of this data is usually low signal to noise ratio. Not only in my own work, others have found considerable success in recent times using these problems. However, the data sets are actually very small. In fact, looking at a non-exhaustive list of dataset sizes in robotics that we have found that they are few hours in the largest. By comparison, datasets in our sister fields, such as vision and NLP, are actually orders of magnitude larger. These fields have mechanical Turk for labeling, but the problem in robotics is data is actually very hard to collect, since experts need to actually show, not just label. So we have created a cloud-based scalable solution to enable large-scale crowdsourcing with only a smartphone and a web browser. It enables full 6-DoF control of a robot in real time. In addition to simulation, actually, we have coupled this with real robots to do more interesting tasks, which are actually much harder to simulate. And Turk has allowed users to interact with robots from any location, such as your home or a coffee shop, or a park or a library, which really encapsulates the spirit of crowdsourcing. Using Turk, we have created 2 datasets, each covering 3 different manipulation tasks and has over 130 hours of robot demos in the simulation case and over 110 hours in the real robot case. So for comparison with existing datasets in robotics, it takes about months to collect these datasets. And we were able to build 10x large datasets within a fraction of time due to scalable crowdsourcing. And now we show some initial results on how we may use this data. We look at 2 of these tasks in simulation. One of them is simple assembly and another one is bin picking. for which the data was collected, we trained them using imitation-guided curriculum learning. We observed that in both of these tasks, given the same amount of compute, the performance of agents improves with more data, while the pure reinforcement learning methods do not make much progress at all. In fact, going beyond where we were using RL, we actually attempt to see if we can use the data purely for in an offline setting. So there is no interaction anymore. And in these kind of cases, we see that looking at tasks such as lifting blocks or bin picking, we find that using clever algorithms such as IRIS or implicit reinforcement learning, and coupled with large data sets, we can actually achieve much better performance than state-of-the-art imitation learning algorithms. So really, the take-home lesson is that more data with structured semantic supervision can fuel robot learning to increasingly complex tasks. And scalable crowdsourcing methods such as Turk enable us to access this treasure trove. So what I've talked about today is really different levels of abstraction from control, planning, perception, and data, and how this can be rolled in with methods in learning or insights in learning. But really, if you take away one thing from today's talk, I would want it to be that learning with structured inductive bias and priors at different levels of abstractions in this pipeline is really essential for us to enable learning for more complicated and sophisticated tasks and to build practical systems that can scale to real-world applications. With that, I'd like to thank a lot of the people who have worked with me over the past 5 years, which were included in the results that I discussed today. And I would also like to thank you for sticking around to show this to the end of this video. Thank you very much.